I work on, this is often from, designed experiments. It may be from physics-based, sometimes well-known, sometimes inexact. It may be from expert opinion. It may be from computer models. It may be from previous experimentation that is relevant but not directly what we're trying to assess now. And so I think we're finding ourselves, as there's more and more data, thinking very hard about how in a principled way do we start to combine that information to support our decisions. And in addition, it becomes interesting because as we are looking at the different sources of information, that different kind of information, they'll often have many different kinds of variability. So if you think about a designed experiment, we have our very traditional sampling variability. If I did the experiment again, I would probably see slightly different information. So there's some variability there simply from taking the sample, as opposed to the kind of variability we might have if we're talking to an expert. That is sort of a different feel for what the variability looks like. And something that, that Bill and Ely said that I think is very true is that Bayesian statistical methods provide a natural approach for combining such information. So let's dig into that just a little bit and think about what that means. Let me start with an example of the kinds of problems that I tend to think about and where a lot of my academic work has focused. And so reaching back even to that very first job out of graduate school, one of the things that I was trying to do was, as DoD, in this case I was working for the Army, was trying to acquire new systems. One of the things that when you're building a new system, the system there is a life cycle for a system. So when you're looking at a system, there is information about the system design. The contractor has evaluated the system. Often there's data there. We've done developmental testing or engineering testing where expert users are trying to assess the system's performance against requirements. Is it the right size? Can it move as quickly as we need it to? And then ultimately, we try to actually test that system out in practice and see if it works in operation. If we keep going and eventually we field that system, we see new variants of the system, we update it, we make life extension. And so the question that has always been of interest, it used to sort of bother me because I was working very much in that operational testing phase where we were trying to take new systems and give them to real users in realistic situations and see how the system performed. Necessarily, those tests were typically very expensive. We would often have lots of soldiers out in the field and we want to do fairly complicated operations and we'd have to do a lot of instrumentation. And so consequently, our sample sizes were often fairly small. And so we were looking at the challenge, and it used to frustrate me as a statistician, and I would say, but we have this other information. This system has been in development, we've done developmental testing, the contractor has information, or if it was a new variant of a system, we've used the system before. Why is it that we don't take advantage of this information that we have? And so what I found interesting as I was putting these questions, these slides together, is I smiled, because what I did is I started, and my first two slides were really very much about the challenges as we're working in very large data environments, about combining information. And then on my very next slide, I go to something where I tend to be working in a very small data environment. And I think what we find, sort of no matter where we're working, is that data is expensive, and good experimentation is expensive. And so, for me as a statistician, the question that I got very interested in was, is there a way for me to do something principled and repeatable to use all of this information and, maybe more importantly, understand the uncertainty that I had in my analysis coming out. So I started doing that, working with air defense artillery systems, and then when I moved to Los Alamos, what I found, I started working on the annual assessment of the reliability of the U.S. nuclear stockpile. And we talk about that process of understanding what's happening there as science-based stockpile stewardship. And really fundamentally what's happened in that arena is since the early 90s, the U.S. has abided by the Comprehensive Test Ban Treaty. So we haven't actually been doing full system testing of our nuclear stockpile. But at the same time, every year there's a requirement for us to assess the reliability of that stockpile. So, if I was thinking about, Army systems, I was complaining about having small sample size. Suddenly when I was in a situation where I had no sample size. But the right answer to this problem is not, I don't know, The right answer is to think seriously about what we do know based on the information that we have. So how do we use the investment that we made in complex computer models? How do we use the previous tests? How do we use our stockpile surveillance, where we bring systems back and take them apart and do very detailed looks at what is happening with the components to start to try to understand what's happening in the stockpile? So again, just to start talking, some of the common threads that we have here, we need to combine many sources of information. I think very typically something that we see across these questions is that we need to use the information that we already have seen to start to think about subsequent data collection. And sometimes, this is a fairly narrow, fairly traditional experimental design, but often it's much more complex, where we are thinking about, there are 15 different kinds of experiments we could do. Each of them has their own factors and conditions. Many of them will exercise different parts of the experimental envelope. And so how do we start to make those trades? And at the same time, we want to use the information that we've already seen to inform how we do that. So that's actually sort of a fun and interesting set of statistics questions to talk about again. And I think the third theme that actually comes out of a lot of what I've just been discussing is often, not always, but often one of the questions that we get asked as we're doing these analyses is not simply, so what's the reliability or what's the state of our system now, but often we're asked to take what we've already seen and to look a bit to the future, to make a prediction. So given what you've already seen, what do you think the reliability of this system will be in 3 years or 5 years, so that we can do some resource planning, so that we can think about life extension kinds of programs? And another thread that's come through with that is, how do we take some of the potentially physics-based knowledge or computer simulation knowledge that we have, and how do we incorporate that into helping to make those predictions? And even if we don't have that information, how do we start to look forward, giving this information that we've combined? So this leads to, for me, very specifically, taking a look at Bayesian analysis, because many of the questions that I've brought up are fairly naturally addressed within the construct of a Bayesian analysis. And so if I'm taking a look at some of the reasons why one might want to think about a Bayesian analysis, and here I'm going to start using some words that are a little more terms of art, a little more technical terms. So the first thing is, it allows for incorporation of prior information. So when I'm talking about prior information, this is where you should be starting to think about, combining the information that I already understand about the system. And so what is it that I already know, and can that inform, my assessment of the reliability or the test design or something like that? I think the next bullet is, if we have relevant data, and that's always a key question, this data may supplement the limited data that I'm able to collect in my current test program. But we have to think about, how do we appropriately use that data? In addition, and again, notice that I'm very careful here, we're using more information. And so this may actually provide improvements in cost. We may be able to do less testing, or in precision, or which is how well we understand our system. I say may, because it is not always the case that when you do new experimentation, it is confirmatory of what you've seen in previous experiments. Sometimes we are fortunate, and our experimentation actually uncovers things we hadn't known before. And so that's something that we like to emphasize, is that using this additional information can improve your understanding of the system, but whether it necessarily provides you the opportunity to do less testing is an open question. And then the other thing I think that is appealing, especially to those of us who really think of ourselves as working within the statistical engineering framework, is that it does actually provide us very strong mathematical and engineering underpinning about how to think about how to do this information combination. Because doing that in an ad hoc way is not something that necessarily lends confidence to the decisions that we're trying to make. Okay, so the next bullet I've got to say is one that the tech person in me loves, but we'll come back to this as we're looking at some examples. One of the features of Bayesian analysis is that it is very straightforward to produce estimates and credible intervals. Again, that's one of my technical terms. What I mean by credible interval is a statement about the uncertainty of my estimate for very complicated functions. And so it lets me answer questions about uncertainties, about predictions, about, so how sure are you that this 95th quantile, that this event that might be in the tail, is unlikely to happen? And so this framework actually gives us some very nice mathematical tools to address some of the real questions that we would like to answer. In addition, and this is an interesting one for someone like me who's really, through my career, has watched the revolution in Bayesian computation, there are a variety of problems for which a Bayesian approach actually simplifies the computations that need to be done. Many times in problems of reliability where we have censored data, taking a Bayesian approach can make the computation much more straightforward. And there are also a variety of the complex kinds of problems that we do where the Bayesian computational tools, actually, even if you aren't doing a formal Bayesian approach, being able to frame the problem in a Bayesian way may make you be able to better do the computation. And so what I have is that fourth bullet is, I think sometimes when Bayesian analysis is discussed, you find that, people can be pretty strong proponents on one side or the other. And what I would argue is that, there's also a very practical, very pragmatic thread that runs through this, specifically in the kinds of statistical engineering problems that we're trying to do, where a Bayesian approach really lets us address the questions that we have about making the best use of information that we have, thinking about how to assess uncertainty in fairly complex situations, and actually getting the computation done. So what I'm going to do is I'm going to start with a fairly straightforward example. It's a little too simple, but I think it's going to let us illustrate some of the basic ideas behind a Bayesian analysis. And as I go through, what I'm going to try to do is talk about some of the strengths and weaknesses that we can see in this analysis. And okay, so let me just get started. So again, I'm going to start off with a problem. And so the question of interest is, suppose that we know that a country, maybe not the United States, is planning to launch a system. And so the question that we have is, how likely is the upcoming launch by country X to be successful? And so this is something that we can certainly frame in terms of a probability. And so if I'm thinking as a statistician, the basic statistics problem that I have is I have some unknown feature of the population of vehicles that could be launched by some country. And I'm interested in trying to make some estimate about that underlying proportion using a sample of data. So this is kind of the standard statistics problem that we have. There's something that we want to know about a broad population. We're not in a position to actually test everything in the population. We take a sample, and from that we want to make an estimate that tells us what's going on in the population. So it's another example. If I'm trying to understand the reliability of the U.S. nuclear weapons stockpile, one way to do that is to actually detonate every weapon in the stockpile. There are a lot of reasons why that's not a good idea, but that would be one way to estimate that parameter. However, one of the things that we know is we have to think of another way to do that. So we want to use other information, perhaps a sample or a smaller subset, to help us do that estimate. So when I'm talking about the probability that I'm trying to estimate, I'm going to denote that by theta. Statisticians like Greek letters often to denote unknown things. And so let's let theta be that probability of a successful launch of a new vehicle. And here's where I'm adding a little bit of information to the problem by, say, an inexperienced country. And so then, again, perhaps I have some data. And during the period from 1980 to 2002, there were 11 launches that I think are relevant. And of these 11, 3 were successful and 8 were failures. So apologies if there are people on the phone for whom this is a data set that they know a lot about. This is just an illustrative data set from an example that was done several years ago. And the data that we might have is we might have a particular vehicle, and again, we would have some outcomes of success and failure. So if I'm working through this problem, thinking about a Bayesian analysis, something that's interesting is that the first step that you take, whether you're doing a Bayesian or a non-Bayesian formulation, is to actually do a very careful formulation. Often a statistician will call this defining a model or selecting a model for the data. And so what does that mean? If I'm using notation, I will typically call something like that. I'll use the notation you see on the slides, which is f of y given theta. And so what does that actually mean? What that means in mathematical shorthand is what is the probability distribution of what I expect to see. So if I am saying my previous data, says I saw 3 out of 11, and what I want to do is I want to try to estimate that probability theta. But if I have some particular value of theta, what would I expect to see if I did 11 experiments? And so this is sort of the interesting back and forth that we're going to have between this parameter, theta, this probability, and the data that I might expect to see if I knew the value of that parameter. And so one way to think about what we're actually doing here, and again, this is a fairly, sort of the simplest statistics model that we all start off thinking about, is suppose that I think about each launch as, again, the technical term is a Bernoulli trial. You should think coin flip with probability theta of success and think coming up heads. And so again, how do I actually use this data that I've already seen to help me estimate theta? So if you're thinking hard about this problem, one thing that comes up immediately as I'm thinking about this is, if I go back and I take a look at these particular vehicles, it might be a bit of a stretch maybe to assume that, the Brazilian system that I have at the bottom of the list has the same probability of success as the Indian system that I have in the middle of the list. And so that's actually really the right question to ask. And that's one of the first, when I talked about being very careful about the modeling, one of the things that I have assumed as part of this model is that there is one probability, theta, that describes the probability of success for each of these trials. And so one of the things that you have to do, no matter what kind of statistical estimation or statistical uncertainty quantification you're doing, whether it's Bayesian or non-Bayesian, is to think very hard about those assumptions. And so for the moment, we're going to take a deep breath and assume that for the moment we're going to decide it's reasonable that there's one parameter, that there's this one probability that I want to think about. But again, if that careful modeling, that being careful about assumptions is something that we're going to come back to a lot. And so here's a bit of math, but essentially the idea for the non-Bayesian analysis, this is often, there are other things that it's often called a classical, sometimes or frequentist analysis. It's that all of the information I have to solve this problem comes from these 11 data points that I have observed. And that's fine, because the analysis that you've done. All of your favorite software packages have the capability to do this problem. There are different ways to think about the estimate, although they all lead you to about the same place. And it's very straightforward to start to understand the uncertainty you have based on that estimate and to actually sort of test hypotheses. So for example, do we think that theta is bigger than 70%, for example? So all of that is pretty straightforward. And most of them lead you to the same path, that for this particular problem, the way that you would get an estimate of theta, which statisticians denote putting a hat over the parameter theta, is we would actually just use the observed proportion that we saw, which in this case would be 3 out of 11. And then we could actually develop a confidence interval using a very straightforward, set of techniques. And that confidence interval would say, well, based on 11 observations, my estimate of that parameter of the chance that an inexperienced nation would have a successful launch is about 27%, but I've just got 11 observations. So if I'm thinking about that uncertainty, I'm somewhere between about 5.2% and 49%. Okay. So here's the second thing that I want to bring up. The first thing that in this assumption, was really, are we thinking about the right model? The second thing that I want to talk about just briefly is that we need to be a little careful as we're thinking about the idea of a confidence interval. And so again, this is the non-Bayesian approach to thinking about uncertainty. And confidence intervals are something that have good properties on average. And so what do I mean by that? If what I've constructed here is a 90% confidence interval, so what I mean is that if we repeat our experiment many times, and every time you watch another 11 launches, you might see 3, you might see 4, you might see 2, you might get different data. But we repeat our experiment many times, we construct our confidence interval. On average, as we repeat those experiments many times, that confidence interval will contain the true value of the population parameter about 90% of the time. And so if that was a little tricky to follow, I'll admit it's a little tricky to teach. And it is fundamentally not the way that most of us really want to think about these interval estimates. I think what's typically easier for people to think about is to be able to make a probability statement. I'd like to say something like there's a 90% chance that this probability or proportion I'm trying to estimate is in a particular interval. And that's actually something that a Bayesian analysis is going to let us do a little more formally. Okay. So to some extent, I just took a quick tour through sort of a traditional non-Bayesian analysis, where we start off defining a model. We then think about how to use that particular data set to get to an estimate. And then typically what we would do is we would use an approach to construct a confidence interval, where that confidence interval will tend to have very good on average properties. So let me change up now and talk about where a Bayesian analysis differs from that traditional classical analysis. And this is going to be where we start to see some of the, some of the features and some of the difficulties with actually thinking about a Bayesian approach. And so the first thing that I'm going to say, and I should have been a little more consistent in my bullet, but the first bullet, data enters through the likelihood function, if I'm translating that, what that basically says is if I go back a couple of slides to step 1 where I say do careful modeling, every analysis, every statistical analysis, being it Bayesian or non-Bayesian, starts here. We have to decide on how we're going to think about the data and the generating mechanism for our data. So, okay. However, step 2 of the Bayesian analysis is a little bit different. And this is where, this is one of the strengths and weaknesses. So we're going to spend a little bit of time on step 2. And so the idea from a Bayesian analysis is that we do have this data that we collected. In our example, we have the 11 observations that we've made. But the argument that you then make in a Bayesian analysis is those 11 observations may not be the only thing that we know about that parameter theta, about the probability that we might see a successful launch from an inexperienced country. Some of that information might certainly be in those 11 observations, but we might also have other information that we understand about that parameter, and we'd like to try to add that to our analysis. And so the way that we talk about doing that is we talk about specifying a prior distribution. So that idea of a prior distribution is being very formal about what other information do you have and what does it tell you about that parameter. And we are going to turn all of that information into, we're going to express it using probability, and we're going to write down some kind of probability distribution on the parameter. And I'll make that much more concrete in just a minute. This previous information can come from basically anywhere. It can come from expert opinion. It can come from historical studies. It can come from previous research or testing, from computer models, from similar systems. Sort of pick your favorite thing. What I will also mention is that there are also ways to express the idea within a Bayesian analysis that, I don't actually really have any additional information. And we can also express that kind of, usually if you could see me, I'm kind of shrugging my shoulders, I don't know. It's a probability. It's probably between 0 and 1. That kind of idea that I just don't have that much information going in. Once I've done this, within Bayesian analysis, the updating is done using something called Bayes' theorem. and we combine the prior distribution that we've specified and the likelihood, the information that we've got from our data. We multiply those together. This gives us a probability distribution about our parameter. That's called the posterior distribution. And so that tells us, after we combine all of this information, what do we think we actually understand about this parameter of interest, about this probability we're trying to estimate. And then a Bayesian analysis moves forward, basing all of our subsequent inference, all of our subsequent question answering on that posterior distribution. Okay, so let me do something to make this a little concrete, because I admit that if you aren't someone who does these analyses routinely, that was probably a little bit abstract. And so I'm going to set up a thought experiment for you guys to think about. And this is going to really illustrate the idea of prior and posterior. And I have borrowed this from what I think is actually a very nice lecture that Jessica Utz gave. So Jessica just finished her term as the president of the American Statistical Association. So she's a well-regarded statistician. And this is a lecture that she gave at the International Conference on Teaching Statistics back in 2010. And I've put the web address up here. These slides will be shared on the site where you all registered for the webinar. So you can pull that web address later or come back to it if you'd like. And Jessica has actually had an interesting thread through her research for a while. And in particular, she's one of the people who has done a great deal of work, you know, some of it federally funded, but trying to understand whether there is any evidence for, well, parapsychology, or more specifically, ESP, extrasensory perception. Okay. And so I'll be honest, this is a video that I have all of my students watch on the first day of, you know, for homework after the first day of my Bayesian class. Because again, I think this is something that, I say ESP and people roll their eyes. And so it's a fairly compelling example. It's something about which most of us have some opinions. And so what Jessica describes in this video is very interesting. She describes a remote viewing experiment and what that means. And again, it's very carefully controlled, and I encourage you to take a listen. But essentially, there is someone who is a receiver sitting in a room with a monitor. And then in a different room, there is a sender. This person has a package of 4 photographs, say, for example, from National Geographic magazine. They're all quite different. The sender picks a packet and picks a photograph, looks at the photograph, thinks about communicating that photograph to the receiver in the other room. The receiver in the other room sketches the picture that comes to their mind, and then these are scored. And so what is sketched by the receiver is scored and by expert raters to see which of the 4 pictures in the packet it most closely resembles. And so if you think about this, this is an experiment that's set up so that you would expect a 25% success rate by chance alone. And if you take a look, there have been many of these experiments, and so in the collection of data, there are roughly 2,124 experiments, and 709 have been successes. And so if we take a look at our very traditional statistical analysis, the point estimate of the probability of success, of the probability of the sender getting something to that receiver, is 0.334, and it has a 95% confidence interval that runs roughly from 0.31 to 0.35. And so the question that I would ask you is, are you convinced that that probability is greater than 0.25, which means are you convinced that there is some evidence that ESP is there and that this remote viewing is actually happening? And so if you think about that for a minute, it's a challenge, because you take a look at the data, and again, Jessica's very convincing when she talks about, how this experiment is run and whether it's well controlled. Many of us look at this and are not convinced. And so let's take a look at how thinking about this problem in a Bayesian setting might sort of model that adjustment that we make in our beliefs based on this data that we've just seen. Because this is a very clear example. When coming into this problem, you are likely to have additional information or expert opinion about the probability that remote viewing is actually a thing, that it's real. And so suppose that you start off as a skeptic. If I'm thinking about this, if I'm skeptical about the existence of ESP, I might say that the most likely probability that something gets from sender to receiver in this experiment is 1/4. I think that what I'm going to see looks like random chance, and I'm actually very sure that the probability going on here is less than, say, 25.5%. And so if I actually code that up in a probability distribution, that's what you see on this slide as the dark line. And so if I take that as my prior distribution, so that captures what I know before the experiment, and then I use Bayes' theorem in the data that I observed, what you see with the dotted lines is the posterior distribution. And what you're going to notice is that I had pretty strong opinions starting out, and the data maybe adjusted it a little bit, but you know, not a whole lot. So if I'm looking at that posterior distribution, I could use that to get an estimate. So I could, for example, look at the mean of that distribution, or the mode, the highest point of that distribution. Or I could even pull out an interval from that distribution where, and I could say I'm 95% sure, given my prior opinions and the data I observed, that this is where I think, you know, the true probability, the true chance of that remote viewing experiment having a success would lie. Now, so if I'm a believer, maybe I think the most likely value for this experiment is 1/3, and I'm 95% sure that the real value is below, say, 36%. The reasoning here I find very interesting is that, you know, if ESP were really a thing, if the effect were really big, we'd all know. So, you know, even though I'm a believer, I don't think the effect is huge. And so again, what you can see here on the same scale that I plotted the previous is that my range, you know, I tend to a priori accept a broader range of possibility, but then the data adjusts my opinion some, but it's pretty consistent with what I actually believed. Another thing that we can do is say, you know, I just don't know. And this is back to my idea of, you know, something not so informative. Maybe the most likely value is by chance, but, you know, maybe there's something. Maybe the real value is less than 0.3. One of the things that you can see if you actually compare the solid line on this plot is it's getting much flatter. That's some of the idea that we try to capture with this idea of non-informative, which is there's a real range of values that are sort of equally likely in my head. And you can see that as these priors get flatter, the data becomes much more informative about what I actually think afterward. And so this plot here is just a side-by-side comparison of the 3 priors that we described, just so again you can see where they're located and how spread out they are, and a look at the posteriors, or what we actually might conclude depending on where we started with our prior information. And so why did I actually go through this example? There's a feature of this example, and many of you are probably sitting here thinking, you know, what this example illustrates is that you can't trust a Bayesian analysis, because fundamentally you can pick whatever prior you want to get whatever answer that you want. And so let me talk about that a little bit, because to be honest, that's one of the primary questions that comes up when people are trying to use Bayesian methods within real analyses. And I think that's really very much worth talking about. And so, I mean, often that's addressed by saying that Bayesian analysis is subjective. And if I'm translating that, I think the primary question is what information or whose information is actually captured in that prior distribution. And what I will say is that to do Bayesian analysis well, prior distributions are not something you just kind of slap down, that you just make up. When Bayesian analyses are done in high consequence decision making, there is a very careful, detailed process of what's called elicitation, or the gathering of that information, the understanding of what's relevant, and that is very carefully modeled. So that's something that I want to mention. You know, I had brought up, as you know, all the way through choices when you're doing analyses of data, we are making assumptions and choices. We are deciding what data is relevant. We're deciding what data should be excluded as not representative. We are deciding that, you know, that was 8 versions of this system ago, and there's just nothing there that is of interest in this particular problem. We're making decisions that, you know, we're going to assume for purposes of this analysis that the probability of each of those shots being a success is the same, what I would argue is when you're using prior information, you are doing something that's very much the same, and that you have to do this kind of careful detail elicitation. The second thing that is a feature of good Bayesian analysis is that they always do a sensitivity analysis. These kinds of analyses are necessarily very explicit about assumptions and very diligent in understanding the impact of each assumption and each source of information on our subsequent inference and decisions. And so if I am making a decision, on the potential reliability of a system, or, trying to predict the reliability of the nuclear stockpile, this is something where I am very careful and I understand how each assumption that I make impacts that decision. But if I'm in a small data situation, sometimes the information that I have might come from an engineer. What you get is, it usually works fine if it's warm enough, but it always has trouble when it's cold. I don't want to lose that information, but I also, if I incorporate it into the analysis, I want to be very explicit about how much of my decision-making is driven by that versus, many thousands of tests under different environmental conditions. So again, that's a lot on priors, but that's something that will typically come up. Another feature of Bayesian analysis, for a long time it was the case that there wasn't good availability of tools to actually do more sophisticated Bayesian analysis. That's changing very rapidly. SAS actually has a proc now called proc-MC, which does a lot of good Bayesian calculations. And the rest of the packages that I'm describing are actually open source. And so there's good availability now of both commercial and open source packages to do these computations. And so the third thing that I want to emphasize, and this is a small point, but I think an important point, is that once you go through these Bayesian analyses, we're in a situation where we don't have to do the fast talking that often comes from a confidence interval. The results that we get from these analyses are probability distributions that tell me about this parameter I'm trying to understand, and so we can make actual statements like, I think that the reliability, I'm 90% sure that the reliability is between 0.2 and 0.3, and that statement has meaning and can be interpreted. So in the interest of time, what I would like to do is I want to circle back to the initial problem that we brought up. And I will have all the slides. What I've got here is just a few words. If you were trying to actually think about this very most straightforward Bayesian analysis, how would we circle back to that launch problem? And so again, we've started out and we've talked about our model. And so we are thinking about each of these data points that we have as having a common probability of success that we're trying to estimate. And then what we have to do is we actually have to specify a prior distribution. So, we come back here. So a prior distribution on what we think that value is. And so I've written out a little bit of the mathematics for those of you who are interested. But I think what I'll do is I will actually show you a few pictures that give an illustration of what this might look like if we did this analysis. Again, I'm going to emphasize that I'm doing this just for illustration to give you an idea of some of the features of how these analyses work. So for example, if I started off, and again on these pictures, my solid line is my prior distribution and my dotted line is my posterior distribution. If I started off and I was fairly confident that the probability of success of a launch was, around 0.8, but there was some uncertainty. If I take a look at that prior distribution, there's still some probability that the probability of success of a launch is about 0.4. And then I saw 3 out of 11 successes. What happens? If I look at my posterior distribution, it's shifted quite a bit to the left. I was pretty confident that my probability of success was high, but now I've seen 11 observations that say, well, you only have 3 out of 11 successes, so how would you adjust to that? And so you can see that that is adjusted to the left. It's not necessarily centered at my point estimate of 0.27, but it is shifted considerably in that direction. If I actually did something that is fairly non-informative or very flat, and this is what's called a uniform prior, so I start off saying, that probability could really be anywhere between 0 and 1. If I take a look at what happens, you can see my posterior distribution. It's centered much more around that point estimate that I have. But again, I still have some uncertainty about that because a priori, you know, if you think about what that flat distribution says, there was a 50% chance that that probability was greater than a half. And now I've seen 3 out of 11, so that's much less likely moving forward, but not completely out of the question. So what I've got on the next couple of slides is now suppose that we multiply the number of data points we've observed by 10. So we've got 110 observations and 30 successes. And what you can see, these are on the same scale, is now that I am much more sure about what I think my actual proportion is. And so it is looking much more like that 0.27 that we would have done in a traditional analysis. Again, if I start from a flat prior, I actually here put all of those posterior distributions on the same chart. What you can start to see is that as I collect more and more data, my posterior distributions start to look very similar. And indeed, that's one of the nice features of the Bayesian analysis setup. If you are in a situation where you collect more and more data, any of the prior information, any of that previous information that you have specified starts to be potentially outweighed by the new experimentation that's aimed very directly at helping you estimate that probability. So that's a nice feature. So let me make a few reflections, and then in the interest of time, what I will do is I will open this up for questions. And then when I post the slides, what I'll make sure to do is include a few slides that talk about some of the directions that this work is going. So one of the emphases that I want to make is that, you know, anytime we are doing quantitative analyses, as much as we don't like it, there is some element of subjectivity here. And I don't think that's a bad thing. I don't think that there's ever going to be an easy button for us to be able to do statistical engineering. There's always going to have to be, what I jokingly say is this is never going to be an analyst-free process. We have to think hard about what the relevant information is, about how the data informs us about the question that we are trying to answer, and about what information that we have that might be relevant to the problem. And we have to think about that and carefully incorporate that into the analysis. One of the features of Bayesian analyses is that they're typically very explicit about the assumptions, especially if you're in a situation where you are using an informative prior distribution, which means something where I'm trying to capture information from outside the specific data that I'm looking at now. That has to be done very carefully. You have to be quite explicit about that, and you have to understand the sensitivity. If we're doing a prior distribution in real analyses, they're carefully developed, and they're developed using related relevant information. Again, it's not something that, you know, would be subject to the, well, somebody made this up, so we got the answer that we wanted. Bayesian analyses do try to explicitly use all of the information, and they often make the interpretation easier. The bad news, what I would say is, you know, the case that we looked at is something that we can actually do with a paper and pencil. Some of these analyses get trickier, you know, again, Bayesian analyses are very possible and very practical with open source kinds of software. And again, so that I think is a good feature. So again, what I would like to do at this point is stop and take a few questions. What I will do is include in my slides, you know, a few pointers towards some of the directions that this work is going. And at the end of my slide set, what I will include are a set of some of my favorite, basically book-length references. So there are a couple things in the popular press or the popular science press that I think really describe how Bayesian methods are useful. There are some very general purpose kinds of Bayesian books and discussions. There are some nice books on this whole idea of how do you develop a prior distribution, because, you know, that's a fairly detailed process. And there's some nice books that lay out some of the computational aspects. And so hopefully for those of you, if I've whetted your appetite on any of those, they'll at least give you a place to get started taking a look at some of the resources that are out there to understand these kinds of methods. And so with that, let me pause for just a moment and let Laura let me know if there are questions that I can address. And so thanks very much.
Thank you. Thank you very much, Allison. And thank you for your excellent presentation. I always learn more every time you present about Bayesian analysis. So I want to encourage folks that are participating, if they'd like to submit questions, they can do that now. through the chat line, and we'll take a look at them and collate them. We only have a few minutes left, and so I would like to maybe offer a few general questions to you, Allison, and maybe give you a chance to expound on a few ideas. So from your experience, I'm interested to know as to what you think is probably one of the most difficult concepts to teach in teaching Bayesian approaches. And then as a follow-up to that, what's maybe one of the most challenging parts to communicate the results, particularly to people who would be unfamiliar with a Bayesian analysis?
Okay. So let me start out with the hard to teach. I'm going to say a lot of the ideas are fairly intuitive. So one of the things that I think, often our students struggle with as statisticians is the confidence interval idea, or the idea of how to think about uncertainty. And so I think that this language of trying to think about uncertainty in the context of probability, the way that we do with this prior and posterior distribution, can actually feel fairly natural. But when I'm thinking about where some of the challenges are, that is a rather different way to think about what's happening. And I think that the students have to do a fair amount of work to try to understand how do I actually build a prior distribution, and how do I think about the sensitivity. I'll be honest, the second challenge is that the computation is not difficult once you get the hang of it, but there's a little bit to getting a hang of it. Because I think in the first way that we tend to teach statistics is many times when we're doing our inference problems, we frame those as optimization problems. So our students are often very, very good at thinking about how to do optimization to get estimates. I think that in a Bayesian approach, it is much more like it's a simulation-based or sampling-based approach, which for those of you all who are familiar with Monte Carlo integration kinds of approaches, it's really a fundamentally different tool set to doing some of the inference. And so once you start to understand what's required of that tool set, I think it, again, is something that, they're starting to be good tools. Communicating the results, again, I think that, there are pluses and minuses on communicating the results. I think that, there's a fundamental issue that sort of cuts across all of the statistics kinds of results, is that often the decision makers we are talking to don't appreciate uncertainty or don't understand that there is uncertainty. They're saying, well, tell me the answer. And but often that answer comes with an interval. We don't know that it is 0.2725694. Maybe we know it's between 0.25 and 0.28, or maybe we know it's between 0.1 and 0.5. And trying to help communicate with decision makers about uncertainty, I think, is a key question. I think then the idea of thinking about effective ways to describe how information besides, the experiment at hand is incorporated and is relevant to the decision making and those sensitivities. Often there's a fair amount of analysis under that hood. And I think this is a challenge broadly across analysis. We've done a lot of math that we really want to talk about. And, sort of the challenge is how do we make the case that the relevant information that we have incorporated has been appropriately incorporated, and that we can understand the impact of that on the subsequent decisions.
Great, thank you. So we've had several other questions submitted. I'm going to, in the interest of time, pick one. You mentioned early on about censored data, and I wondered if you could expound. The question comes to explain that a little bit more, what you mean about applications of a Bayesian approach to censored data.
Sure. So censored data is something that comes up a lot in studies of lifetime. So how long does something last? And so suppose that I have a light bulb and I turn it on, and I come back once a day at the same time to look and see if the light bulb is still burning. So if it's burning today, but it's not burning when I show up tomorrow, I don't know exactly what time the light bulb burned out, but I do know that its lifetime was sometime, it was alive the last time I looked, and it's not still burning now. And so that's the idea of censored data, which is that I have some information about the lifetime. In this case, it's an interval censored value, where I know it's it lived sometime, yesterday, but not today. And there are a variety of ways that that kind of data can be censored. And so when you have to incorporate that, because you didn't observe an exact value for the lifetime. Instead, you observed partial information about that lifetime. And so particularly in reliability analyses, it is a feature that in a Bayesian analysis, and given the inferential procedures that are used, that kind of information, that kind of partial information, is actually very straightforward to incorporate into the analysis.
Excellent, excellent, thank you. And so we've had some other questions, but I'm going to have to move on in the interest of time to close this. I would encourage those people maybe to reach out and contact Allison directly. So to wrap up today, we are glad you joined us, and we certainly hope that you've enjoyed today's webinar. We want to definitely thank Dr. Wilson once again for sharing her expertise in Bayesian analysis. And if you're interested in learning more about statistical thinking and methods and how they're impacting real-world problems in national defense and aerospace, we'd encourage you to consider attending the 2017 Science of Test workshop. And that slide is up right now. The website and information, it's going to be held in Springfield, Virginia, and it's being jointly organized by NASA, the Director of Operational Test and Evaluation, and the Institute for Defense Analyses. And for a little quick background, this is a series of meetings that started in 2011, and last year's meeting we were glad to host over 200 participants, and it serves as an essential part of our productive collaboration. It's designed to bring together practitioners, analysts, organizational leaders, and statistical experts for a 3-day knowledge exchange, and there are opportunities to attend outstanding short courses, share common challenges, and learn new skill sets. And just as a bit more of an explanation, it's not just another conference designed exclusively for statisticians. Rather, we're trying to create an environment for multidisciplinary knowledge exchange that will produce greater organizational impact of statistical methods. So if you don't consider yourself a statistician, then this is a meeting you might want to consider attending. And there's more information on the website. The first day we offer 5 all-day short courses, and the following 2 days are a mixture of over 50 breakout sessions with both leadership perspectives and mini tutorials. And it involves speakers from across multiple government agencies, academia, and industry. So for more information on that, we direct you to the website, or you can contact Laura or myself. And as a final note, early registration for that workshop ends on February 28th. So once again, we want to thank everybody for joining us today. Thank you, Dr. Wilson, and we hope you all have a pleasant afternoon.